Hey everybody. So this will be a quick video on the anatomy of the ear. So we're going to start with the outer ear, go to the middle ear. All right, so let's get started. All right, so here we see a diagram of the entire ear largely, but what I'm going to do is I'm going to focus here on the outer ear, and then we'll move to, and then I'll highlight a few points here, but we'll move to it. Right. So the outer ear is this fleshy outer part, right, the part that most of us think of when we think of the ear, right? And that's called your pinna. Well, the canal then, the ear canal, is the uh, tube that pressure gets routed down. The pinna helps focus those uh, pressure waves down the ear canal. It also helps with echolocation. Um, and then once the pressure wave moves in the ear, it then hits your tympanic membrane, also known as your eardrum here, which then, as you know, we were talking in the last video about resonance, it then reflects back approximately 3,000 pounds. So that's the outer ear. Now the inner ear is this area in here. Now the inner area primarily consists of a cavity that's largely empty except for these three bones. Um, these three bones are your hammer, anvil, stirrup, but that's uh, also the Latin names are the malleus, the incus, stapes. Okay. Now the point of these three bones is to amplify the sound hitting the eardrum. So when the pressure wave comes in and it hits the eardrum begins to vibrate, kind of like the speaker does. That then vibrates the malleus, which vibrates the incus, which vibrates the stirrup. The stirrup is then attached to a membrane right here on the cochlea of the inner ear called the oval window. So the tympanic membrane moves in and out like a speaker, moves the malleus, incus, and stapes, and the stapes moves in and out, moving the oval window. But the frequency of the sound, um, the sound is amplified through the bones. And the reason for this is because on the inside of the cochlea, where the hair cells are that the stereo the receptor cells for sound, they're suspended in a fluid. Well, that fluid has a different, it's viscous, all right? And anytime you change uh, mediums from one medium to another, you get interruption of the sound. So, uh, one second, guys. Hey guys, sorry about that. So let's get back to it. So again, these three bones amplify the sound largely because when a pressure wave transitions between mediums from air to water, whatever transition it's making, it loses some of its amplitude. And so if the pressure wave were to affect the oval window directly, the sound would be largely muffled simply by the transition from air to the fluid inside the cochlea. So the three bones there amplify the sound so the resulting sound that ends up in the cochlea where the auditory receptors are is loud enough to be perceived. So that's the outer and inner ear. Now the outer and middle ear. Now the inner ear is largely just this cochlea. But we're gonna zoom in here and look at what's inside the cochlea. Now remember that the stirrup, you can see it here, attaches to the oval window. Well, remember that all of this is filled with fluid. All right. So when the stirrup vibrates pushing and pulling on the oval window, it causes a disruption in the fluid. Now, the hair cells, well, I guess before I go into that, I will say that this is a side view of the cochlea. If you look from the front, you will notice that there's three chambers. And the chamber that is most important for us is the cochlea, the scala media here. Because here in the scala media, you have the basilar membrane, which has the receptor cells embedded. Now, on top of so collectively, this pectoral membrane, the hair cell layer, and the basilar membrane, collectively we call this the organ of Corti. And here is where the action of auditory transduction happens. So here, when the disturbed fluid, so the change in the fluid pressure, moves to the basilar membrane, it starts pushing these hair cells back and forth. And the basilar membrane ends up actually moving up and down, while the tectoral membrane ends up moving back and forth. And so what happens is that you have these hair cells that then get pushed back and forth by the pressure wave moving through the fluid. Now you might note that some of these hair cells here on the tectoral membrane, on the basilar membrane, they look like they're in the tectoral membrane, and they are. Now those don't move back and forth. Those don't transduce sound. It's the ones that aren't attached. It's the hair cells that aren't attached to the tectoral membrane that actually transduce the sound. So how does that happen? How does transduction happen? Well, here we have a zoomed in view of a auditory receptor cell. Now, so it says it's labeled inner hair cell, inner hair cell. That's because the outer hair cells are the ones that are embedded in the tectoral membrane. Now, they help amplify the sound even more. So they will actually, it's really cool, they'll actually change shape. Remember how the basilar membrane goes up and down? The outer hair cells will actually change shape to elongate and retract. When it retracts, it pulls the basilar membrane even further up, and when it extends, it pushes it even further down. So it's amplifying the sound again. Or you have another mechanism amplifying the sound. But the inner hair cells, where the actual transduction happens, have these cilia, these stereocilia, on the tips. Well, these stereocilia have sodium channels on the tips, and each cilia is attached to the sodium channel of the neighboring cilia's sodium channel. So when the cilia are pushed in one direction, there's tension is put on those tip links. And when that happens, it pulls open the sodium channels in the neighboring stereocilia. Sodium then floods into the neuron. Then when the hair cells sway back in the opposite direction, the tension on the tip links relaxes and the sodium channel closes. Well, when it's swayed in the direction that pulls the sodium channels open, the sodium floods in, causing an action potential to occur. And that's how, and then the action potential then proceeds, the electrical signal then proceeds on down the auditory nerve. Now, humans can only perceive between 20 and 20,000 hertz. The average adult can't even hear that wide of a range. Like for example, the high end of my hearing range is 13,000 hertz. And you can all check your own hearing range if you want to. There's a Whisper app or a Cricket app that you can go on and you can change the hertz frequency and you can play it and you can see at what point you quit hearing. Now, even though we have this wide range, the majority of what we hear is from 2,000 to about 4,000 hertz. So even though, as we get older, we lose a lot of the high end, it doesn't really matter because we don't use it much anyway. And so it doesn't affect our day-to-day lives as badly. So we spend most of our day listening to things being played at between 2,000 and 4,000 hertz. I mean, even the highest pitch key on a piano is like 4,300 hertz. So we don't have most of the things we hear in our daily life don't vary a whole lot, but we do have a wider range, if need be. Um, Now, how do we hear this whole range of hertz? Well, one explanation for the way we hear each hertz or this full range is place theory. Now, place theory argues that depending upon which stereocilia along the basal membrane are activated, determines what pitch we hear. And so, here's the oval window, and here's the apex of the cochlea. If we go back to look at the cochlea, you've got this spiral pattern. That's what's causing that spiral pattern in the basal membrane or basal membrane. So as we move up towards the apex, the stereocilia become less and less rigid, meaning it takes less movement, it takes less vibration to move around. So I guess you could, well, it actually says it right there. The stereocilia towards the apex, towards the center of that spiral, they're more floppy. And the stereocilia towards the opening of the oval window, they're stiffer. So for the stereocilia towards the opening of the oval window, it takes a higher pitch to get them to move because they're so rigid. Whereas the stereocilia close to the apex, towards the end of the spiral, they're more floppy, and so it doesn't take as high a frequency. And so, according to place theory, the pitch you hear is determined by where the stereocilia are that respond first to the sound. All right, to the sound wave. So that's one explanation for how we hear pitch. So that is what I wanted to chat about in this video. So again, in this video, we talked about the anatomy of the ear, and we talked a little bit about pitch perception. And I'm gonna have a couple more videos about hearing, but that is it for this one. I'm sorry for the skip. My roommate for the conference popped in, so I hope that doesn't cause too much trouble. I guess I can look at the video here to see what it caused. Hopefully. But anyway, as always, if you have any questions, let me know. If not, anyway, if you have any questions, let me know. If not, catch you later. Yeah.